So the object is to try to compute this, and so I'm giving you the modern, say. So of course, in terms of something simpler, so in of Chern classes. So both those things are modern things. And you have to have cohomology, you have to have classes, and you have to know about Chern classes. So what I want to do first is give you an example which is enough for most of the talk. And so where all this comes from, so let me give you ancient history. I guess the first thing that we really call this thing is Bazoo. So that's, I think, 1779. In fact, it really goes back to Newton, a long time before that, who observed that if you have two plane curves, the number of points in the intersection is the product of the degrees of the two curves. And Bazoo generalized it. But let me say it in this language. What he said is if you have so F1, say, up to FB are at least general. So I'm going to be pretty vague about what general means, but general homogeneous polynomials of degrees, say, let's call them A1 up to AD. So in some variables, x naught up to x, say, capital N. So what we would say in modern terms is that the degree of the zeros of that, so F1 up to FD, so you look at the zeros of a bunch of homogeneous polynomials, so in the corresponding projective space, so this is the compactification of Cn, that this thing should be, is the product of the degrees. So he didn't actually do that. What he did was say that when D was equal to N, he said the number of solutions of these equations is the product of the degrees. And in fact, if you look, it's a wonderful book. It's several hundred pages. There's exactly a half of a page in geometry. And that half page says 3 quadratic surfaces meet in 8 points. And all the rest is algebra, trying to find algebraic ways to solve equations. But we call it Bazoo's theorem. So let's say it in modern terms of this. What we would say is that the cohomology of projective space is a polynomial ring in a variable h, where h to the n plus 1 is equal to 0. And h, in fact, is the class of a hyperplane. And what we would say is that the zeros of that, this v, right, is the product of the ai's times h to the I, or the product of these things in that ring. And in fact, in modern terminology, that's the product of C1 of O of AI. So that's the first Chern class of the basic line bundle on projective space. And a lot of what we've been doing in algebraic geometry since, of course not all of it, but pretty often we're reduced to finding subvarieties of some moduli space of some kind, and we want to find formulas for it in terms of simpler things like Chern classes. But in fact, this case of projective space is really enough for most of what we're doing. So this is what we call the trivial case, is when you have a subvariety of projective space that's defined by the number of equations that its codimension should be, and then the answer is as simple as it could possibly be. So the interesting case is when that's not happening, and in fact...
So this degree here means the number of points, or what is this?
So of course, this is one way to say what the degree is. So what the degree is, and if you look at that, one way to say what the degree is if you intersect this with a hyperplane of complementary dimension, that the number of points will be this product of these degrees, okay? Which you can also see from that equation. You intersect with h to the n minus d. So and of course, they knew that there were subtleties. For example, I mean, surely Newton knew that if there were tendencies. That's not the actual number. You have to count somehow, and then multiplicities, and that's a long story in commutative algebra. But the subject really became substantial. So starting, I found an old paper by Cayley in 1849, and there's a whole series of papers all through the last half of the 19th century, and it ends with Giambelli in I think there's a series of papers, 1910, 1912. Right? And a whole bunch of people in between. About half of them you've probably heard of if you're a geometer, the Segres and Schuberts and such, and quite a few algebraists you probably haven't heard of. And they all looked at this situation. So A is going to be a matrix of homogeneous polynomials. So these Fij are homogeneous. So this is an n by n matrix. And there's a locus in projective space. So if I take an R that's less than m and n, there's the locus where the rank of A, well, I'll just write this way, is less than or equal to R. So at each point of projective space, you feed that point to the polynomials, and you compute the rank of that matrix. And if it's less than or equal to R, you're in that locus. And that's a subvariety defined by polynomial equations. All the minors have to vanish. Right? Well, in fact, you have to be a little careful. If the Fi is homogeneous, I want to compute all the minors, and they have to be homogeneous. Right? And that's not automatic. Right? So you need some conditions on the degrees, and I'll say it in a way that's compatible with modern terminology. You assume that there's some integers. Take them positive if you like. So the degree of each Fij is Ai minus Bj. So then you see that if you try to calculate any minor of this matrix, it's going to be a homogeneous polynomial. And so Cayley realized that. Okay. And the question is, what's the degree of this thing?
Is that the necessary and sufficient condition?
Essentially, yeah. If you, no. You'll see later a more natural way to say it. So the question is, what's the degree of this? So one thing that's quite an easy exercise in beginning algebraic geometry is that the codimension. So of course I'm assuming they're reasonably general. The codimension of this, it's not completely obvious, but it's not really hard. It's m minus r times n minus r. But the key thing is this is a fairly small number, and the number of equations defining it is a huge number, right? All the minors. So they're right? M choose r plus 1 times n choose r plus 1 minors. So it becomes a real challenge. And in fact, one thing that's fun is try to imagine how they did it. I mean, here we are, we have modern tools. How did they do it in 1849? And Cayley gave quite a few answers, and there are dozens of papers, and finally the general case was done by Giambelli. I don't know how rigorous I know some of the early papers are not very rigorous. Whether you could get a modern proof out of their papers, I'm not at all sure, but certainly the results are there and they're correct. And here's the answer. So, I mean, in other words, the degree, we want to calculate the class of this locus. And you take C to be the product of 1 plus the AIH over the product of the 1 plus BJ H. Okay. So this goes from 1 to m, and this goes from j equal 1 to n. And you write this out to 1. So these C's are symmetric functions in the A's and B's. So like C1 is the sum of the A's minus the sum of the B's. And C2 is a more complicated thing. Okay. And then the wonderful answer is that this thing is given by a determinant, and you take Cn minus 1 and put it down the diagonal, and then you increase the subscript by 1 when you move to the right and decrease by 1 when you move to the left. And you take an n minus r. So, in fact, Cayley did the case when r was 1 less than m and n, the minimum. But the general case that's in Giambelli, so I'll write it. Looks a little funny maybe, but so it's an n by r matrix. You put these C's in the matrix in that way, and out comes this complete, beautiful closed formula for this thing. So Cayley had the case when, so say m is less than or equal to n, and r is m minus 1. So then it's a 1-by-1 thing. It's just n minus m plus 1, and it's that coefficient of this thing. Right? But again, imagine, put yourself in 1850 and see what on earth would you do to prove something like that? Right? It's defined by a whole lot of equations. It's not. It's quite. No, this. So I'm putting them in here. Yeah, so C1 would be the sum of the a's minus the sum of the b's times h, right? And C2 would be another polynomial times h squared. And
so that is homogeneous in the A.
Right. So I'm trying to make it kind of compatible with that. So this is the basic formula that came from that exciting period of algebraic geometry. These polynomials now are determinants like that are often called sure determinants. There are quite a variety of them. I think, in fact, these formulas came before sure did, but that's typical in the subject. So the next part of this story is the Tom Porteous. So this is the 1960s, and so René Thom looked at the situation where we have two vector bundles on a variety. Say this one has rank m and this one has rank n, and we have a map between them. So they're complex bundles, but a general map. In fact, he was in the C infinity category, and you have a locus, omega r, where the rank of phi is less than or equal to r. So it's a set of points in X where the rank is less than or equal to r. And that's the subvariety of codimension, in fact, m minus r times n minus r. And of course, there's an obvious example. So that is an example of this, right? So the example is that X is projective space, right? And, well, you have a map from direct sum of O of bj's to a direct sum of O of ai's. If you know about those bundles. So, and a matrix A of those degrees is exactly what it takes to give a map from this thing to that thing, which kind of explains where that ai minus bj comes from. Right? And Tom looked at this and he said he wanted to find a formula for the class of this thing in the cohomology. And he said, there must be a formula for this in terms of the Chern classes of E and the Chern classes of F. Okay? And why is that? Doing this is compatible with pulling back. And there are universal places where you find bundles. They're on Grassmannians. And on Grassmannians, so you'd have like a product of two Grassmannians where this would be the tautological bundle on one and this on another. On that space, if you look at this question, there aren't anything but polynomials in the Chern class of those bundles. Right? And if it's the kind of universal formula that's going to pull back, there has to be a polynomial in terms of the Chern classes. Well, if Tom had known this story about Giambelli, he wouldn't have had to ask Porteous and other people, what's the formula? Right? We just wrote down what the formula is. Right? So the answer, which is often called Tom Porteous formula, but it's pretty ridiculous to omit Giambelli's name, is it's the exact same determinant, right? C n minus r plus j minus I, exactly the same. But what's C? Well, you just have to take the total Chern class of E and divide by the total Chern class of F. So that's the formula that they proved. I should say they proved that only with very strong transversality conditions on the map. So, it not only had to be transversal to every possible locus you would be interested. So the ones you're interested in are locus of rank R, but it had to be as general as possible with respect to all possible ranks. And so, for example, well, one of the main applications of this formula is if you compute the right-hand side and it's not 0, right, then that implies that the left-hand side is not empty. Right? That doesn't follow from that theorem, because they have to assume really transversal. Even the parts where it's not empty, it has to be transversal. And in fact, there's a beautiful paper that Kemp and Laxoff wrote, I think.
Transverse in things of dimension R, couldn't you just use a relative transversality to fix up everything else without changing the
I don't think so. I don't. I don't know. I know people tried. So one of the motivations for doing it in an algebraic way was to get around that problem. So I don't think anybody found a way to do it directly.
In the case of your example, is it stronger than the general that you didn't really tell us about on the
Yeah. So let me give you the right. So there's a beautiful paper in many ways by Kemp and Laxoff. And so first they made this all algebraic. Right? So they proved that it's one way to say Tom-Porteous is true whenever the codimension of this locus is equal to m minus r times m minus r. So it's always less than or equal to that. That's a general simple fact. And whenever it's equal to that, in fact, you don't even need it to be irreducible. Just if, as a set, it's equal to that. You can do if it's not an irreducible subvariety, there's a naive way to assign irreducible subvarieties to it with multiplicities given by length. You just assign those numbers, and you get a cycle of this omega r, and that cycle is always given by this Chern class. But the proof used all kinds of new ideas. For example, the fact that a general locus like that is Cohen-Macaulay is a key part of that proof. I think that's the first time anything like Cohen-Macaulay ever appeared in, nothing in the question says anything about Cohen-Macaulay. So they brought modern commutative algebra techniques into the story. They also did another important generalization. So instead of just having maps like that, let me use subscripts for dimensions, or for ranks. So I have a map of bundles, and I have a bunch of subbundles of the first bundle. And I look so the locus we look at now says the dimension, I can say it in terms of easy way to remember, the dimension of kernel of the map from Fni to Em is greater than or equal to I for all I. So again, that's given by minors. And they gave a formula for this locus, and it's another determinant very much like that. So here I write down again, I'll write it. C lambda I plus j minus I of E of the E minus F Ni. And let me tell you what the lambda I is. It's not terribly important, but just the shape of the formula. So lambda I is m minus Ni plus I. One reason I'm writing the explicit formula is it's another determinant. Right? It's a sure type determinant. One interesting thing about it is if you write out these things in terms of the A's and B's like we did before, these are what are called generalized factorial sure functions. they've been discovered about a dozen times since then, but they should be called Kempf-Laxoff polynomials, but nobody ever does. They're important polynomials in combinatorics. And so why was this better? Well, if you're in the Grassmannian, these would all be trivial bundles, right? And a locus like this is exactly what's called the Schubert variety. Right? And this gives all the formulas for all the Schubert varieties. So these, I'm sorry, this E minus F that's my abbreviation for this thing. And so in the case where these are all trivial bundles, you don't need this, and it's polynomials in these things. So it's formulas for all the Schubert varieties in terms of Chern classes of the quotient bundle and the Grassmannian. One thing I'm quite sure they didn't notice is even if all these bundles are trivial, but you have a action of a group on them. So your varieties are Grassmannian, the general linear group acts, in particular the diagonal torus will act on it. Right? And they'll act on these trivial bundles in a non-trivial way. And if you apply this formula, what you get is formulas for the equivariant Chern classes of this thing and the equivariant cohomology of the Grassmannian. I say I'm quite sure they didn't know that, but they had a lot of what they did came to fruit quite a bit later. Okay. Yeah, their proof also is the first one I think that modern algebraic geometers can understand. That they did it by the problem is you're on something's defined by the wrong number of equations, and what you almost always do now, ever since their paper, is you go to some space lying above x, and up there you find another locus. So you find something like x prime to x. So this might be a much bigger space than this, but up here you find a locus that maps birationally down to omega. But this one up here is defined nicely by the right number of equations. So technically what that means is it should be the zero of a section of a vector bundle of the right codimension. And that means you know the class of this, and the class of this pushes forward to the class of this. So you need to do some clever Gießen algebra to figure out how to push forward the formula. And that's what we've been doing ever since in this story. So it was really a key paper. And I should say they also, together with Kleiman, gave some beautiful applications of this. In the sense that I said, so now it's without any doubt, as soon as this polynomial is not zero, this locus has to be non-empty. Right? You can't say what dimension it is even, but it has to be non-empty. Right? And they applied that to prove the existence of special divisors, which has been an open question for years. So for example, then for a Riemann surface, you know, whatever genus it is, it can be written as a branch covering of the sphere. Well, how many sheets do you need? And the answer is about G over 2. But it's a highly non-trivial thing, and it follows from this story. There are other proofs, but okay. So maybe I'll go. Yeah. So Lascaux and Schützenboucher in 1982 Lascaux certainly knew about flag varieties and talked about them sometimes, but the papers they wrote were entirely combinatorial, in fact, pretty hard to read, but they constructed what they called double Schubert polynomials. So they're in a polynomial ring with integer coefficients, and by that I mean infinite number of variables, but each one of them is a polynomial. So those of you in combinatorics, watch out. We're not in some ring of symmetric functions with infinite numbers of variables or anything. They're finite polynomials. Right? So for each w, well, in a symmetric group on any number of variables, it's a very definite polynomial with lots of marvelous properties. And fortunately, MacDonald wrote a nice book about them, which is much more readable than their papers. But the ones where you set like y variables equal to 0, they're called sometimes as Schubert polynomials. And double means you have both the x and the y variables. So what are they all about? Well, let me try to tell you the whole, maybe not the whole package, but a lot of the package of what we have here. So the zero, well, I'll call it the first one here, is that it's homogeneous polynomial of degree the length of w. So every permutation has a length. It's the number of inversions, the number of I less than j, such that wi is bigger than w of j. And so you get homogeneous polynomial like that. In fact, that'll follow from one of the later properties, but I need it stated separately. And here's what they all are, I think. Yeah. So let me tell you what one of them is. So this is what's called the W of longest length. Everything is greater than the next one. So that's the biggest one. So this polynomial is the product over I plus j less than or equal to n of xi minus yj. And it's this minus sign in their polynomials that explains why I had a minus sign in my original Cayley story. Right? So that tells you what that one is. And the second one tells you what they all are. So if w is gotten from another permutation by multiplying by a transposition, so Si is the standard transposition of I and I plus 1. And if this one is longer than this one, that means V of I is bigger than V of I plus 1. So when you do that switch, the length goes down by 1. Then I know what the Schubert polynomial for W is in terms of the Schubert polynomial for V. And what's di? Di is a difference operator. So di of p. So p is a polynomial in two sets of variables. And it's gotten by taking, I take p of xy, and I subtract off p of, I just interchange the places of xi and xi plus 1. Ignore the y's completely. Right? This is if they weren't there. They're like scalars. And once I've done that, of course, that'll make the difference divisible by xi minus xi plus 1, and so we divide. And the degree goes down by exactly 1. And the claim is that this is true. In fact, the claim is also that if v of I is less than v of I plus 1, and you do this, you get 0. So it's kind of part of the package. But this is all you need. So A and B completely determine all the Schubert polynomials. Right? If you take a W and Sn, you can start from this one and do this certain number of times and take that top one and hit it by these difference operators, and you'll get every Schubert polynomial. How long it'll take you, it could be a lot of algebra in a big symmetric group, but it's completely explicit. And they proved many wonderful things about these. I'll only state a few of them. So, of course, again, the name is always poor, I think. The one thing you can be sure about these polynomials is that Schubert didn't have anything to do with them. But they do have something to do with Schubert varieties. And Here's one thing that's not obvious from this definition, but it's an important fact. So is it's stable. And what does that mean? Well, that if I take W and Sn, that this polynomial is independent of n. Okay? So I take a W that happens to be an S6. It says I can start with this guy with 6 of them and work my way down. I could also regard it an S17 and do the same thing, and I'll hit exactly the same polynomial. So, but again, each one's a finite polynomial. They also have a symmetry, which is even less obvious. Is if I take a permutation and take its inverse, what happens to this thing? And the claim is that it's exactly sigma W, but with x and y interchanged, and because of this sign choice that we made, we have to put minus signs in it, right? So you can at least check that for this top one, right? If W is equal to W inverse, and that's certainly true there, but it's true for all of them. I think one thing remarkable is if you compare this with the 2b there, right? It's saying to get all these polynomials, you ignore the y's completely, right? Just think of the x's, right? And grind out, and you get this polynomial. But it says that's a complete illusion, right? This says you could have done exactly similar thing for the y's and ignored the x's, and the same thing is true. So it's quite a remarkable property. And there's some positivity. So I'm stating algebraic properties first. And so there are actually two kinds of positivity. The first one is a kind of an algebraic one. It says these polynomials are positive in the monomials, so, well, in the xi's and the minus yj's. So again, that minus sign keeps showing up there. It's not quite obvious from this. When you take a polynomial that's positive like that and do a difference operator to it, it's not preserved necessarily, but these are all preserved. That's not so exciting, but historically it was important. Here's one that is extremely exciting. And if I take two of these and multiply them, it's quite easy to see that the product can be written as a linear combination of the others. In fact, one thing I probably should have said is that these give a basis for all the polynomials in two variables over the polynomials in one variable. So you can kind of see there, each one has a different monomial at the top. Anyway, it's not hard to see that you can write this out like this. So this will be a homogeneous polynomial of degree the length of u plus the length of v minus the length of w. And so the c, u, v, w's are homogeneous in c of y. That's easy to state, at least, and easy to prove. But in fact, they're positive in the variables. So y2 minus y1, y3 minus y2, and so on. And this is a beautiful, quite deep theorem of Bill Graham. And one reason I'm stating this is what's completely, I'm going to run out of, kind of trying to hope I could have everything on the board, but let me just say, it's quite open as, so what are they? So, nobody knows. So you give me three permutations, and we can write down a polynomial. Nobody even has a guess as to what that polynomial is. So a very special case is the ones of degree 0. So when the length of this plus the length of that is equal to the length of that, these are just numbers. Right? And nobody even has a guess what those numbers are. So they're positive numbers, and nobody knows what they are. That's quite astounding. So if you take the special case of the Grassmannian, so I'll explain how this relates to Grassmannian before. So some of these are, in fact, essentially the Kempf-Laxoff polynomials. If you write out those, in fact, those were studied. They were studied by Moliff and Sagan, and they gave a formula for them, which didn't look positive. And amazing, they were combinatorialists, and they didn't notice it was positive. They had positive and negative terms. And then Graham proved his general theorem, I think, in about 2001, around there. And then Knudsen and Tau wrote a marvelous paper where they gave formulas for some of these, the Grassmannian ones, in terms of what they call puzzles. And I recommend it to anybody. It's a great paper. But these polynomials, you take the 3 permutations to put numbers on the outside of a triangle, and then you make all possible puzzles with certain kinds of pieces with those outsides. And every time you use a certain kind of a piece, you write down a monomial in one of these. And you make all the puzzles and add them all up, and that's the coefficient. And so people have been dreaming ever since that there should be something like that. In general, nobody can do it. In fact, amazing. No, there isn't even a guess. So, yeah, Anders Brook, someone said there's something about his paper today. So he did it in the case of 2-step flag. So they did 1-step flag. So it's known for 1-step and 2-step. And there's not even a guess for 3 steps. I mean, it's, OK, so geometry. So this is when I got into this game, although I was interested in it for a long time. About 10 years later, here's the geometry behind this. So you're given vector bundles. And I'll use the same convention. So the subscripts tell you dimensions. So I've got bundles of rank n with a whole flag of subbundles, and another bundle of rank n with a whole flag of subbundles, but I take the corresponding quotient bundles. And for W and Sn, there's a locus corresponding to this, omega W. And it's given by a whole bunch of rank conditions. It says the rank of the map from the qth one over here to the pth one over there is less than or equal to a number that you get from W. In fact, it's the number of I less than or equal to P, such that W of I is less than or equal to Q. In fact, if you go back to the very first case we looked at, the Cayley case, right? You've got a matrix. And what you can take for these Fs are the think of this as direct sum of line bundles, right? And you have another direct sum of line bundles. This thing from FQ to EP would be exactly the upper P by Q corner of this. And it should be the less than or equal to the number of those things. If I take my permutation and write it like this, say, well, yeah, I don't have enough spaces here. I'd have to go like that. What it would say, you look at the rank of the upper corner should be like the rank of the thing from this 4 space to this 2 space. Well, 2, that's no condition, right? But if I look at the 2 by 3 one, it says the rank of this locus should be 1. Right? And generally, you get a whole slew of rank conditions, so n squared of them, right? For all these things. And each one of those, of course, is defined by a whole slew of rank, minors. So it's a locus defined by an enormous number of equations. In fact, the codimension is the length of W. And the theorem is that the formula for this is exactly the double Schubert polynomial of Lascaux and Church-Imposé, where what are the x's? So the xi is the first Chern class of the quotients here. So it's C1 of the kernel of EI to EI minus 1. That's the line bundle. And YI is C1 of FI over FI minus 1. So this contains the last Kemp-Flaxoff story when I just have one bundle over here. And of course, Porteous is really when you just have a map and no subbundles. But this formula also completely determines the Schubert polynomials. There's a unique polynomial that does this. In fact, if you go back to the Cayley situation, instead of just looking at single rank conditions, you look at rank conditions like this. The Cayley situation completely determines these double Schubert polynomials. Historically, what happened is people noticed that, again, if you take these to be equivariant vector bundles, trivial bundles with a torus action on them, and these to be general geometric bundles, these give you formulas for equivariant classes of these things. And that historically played an important role. OK, so yeah, I guess I can take this one. So, in general, these polynomials are complicated, but some of them are determinants. So they were created with their terminology. Not like most mathematicians saying normal or regular or something. They call them vexillary. So certain W's have this double Schubert polynomial as a determinant of certain C's. So, and these W's they call vexillary. So for those who know, vexillary, the technical term is that W avoids the pattern 2, 1, 4, 3. So you never have small, smaller, big, and bigger going along like that. All of those have determinantal formulas, and essentially none of the others have at least nice systematic determinantal formulas. And the other is something that I did it while I was doing this geometry, is there. As I said, these are defined by an enormous number of equations, but in fact, that's pretty much an illusion. What you can do in this case, for example, you take each one of these dots. So this is the permutation 2, 4, 1, 3, 5. Right? Take each one of the dots and cross out everything below it and to the right of it. Maybe I should do it this way. Okay. So we're left here with three boxes, and those are the only ones that are essential. In fact, the only ones that are essential are the ones in the southeast corners of those, the ones that are left. So this locus, although it was defined by 36 conditions, it really just says this upper 2 by 1 block is 0, and this upper 2 by 3 has rank 1. And in general, there's a notion like that. OK. So, yeah, we've got, I don't know how much downtime I get, right? But, yeah. So I think it's pretty clear. This is type A, so the GLN story. And the question is, what about the other types? So I'll just do this very briefly. Classically, they looked at some of these. So for example, if you look at the matrix A at the beginning, and you say it's equal to its transpose, or minus its transpose, those are not at all general matrices anymore. And in fact, you have to find very different formulas for them. And they did. And modern people did too. Josefiak, Pagash, and Lascaux, and Harrison too. And there's quite a literature on maps of. So this thing corresponds to modern terminology as you have a map from a bundle to the dual bundle, and it's a symmetric or skew symmetric map. What are formulas for that? And we found a lot of formulas for these things. Well, let's take type C. So in fact, the claim is that you can do all of this in all the classical types, A, B, C, and D. That's the goal of the last 20 years of work in this. So what is type C? You have a vector bundle of rank 2n and a skew symmetric form with values, say, in the trivial bundle, which I write 1, and non-degenerate skew form. And the typical kind of thing you do is you have E and F are maximal isotropic. So the form vanishes on those subbundles. And in fact, Joe Harris asked this question. I don't have a date because it was in the common room, but you look at omega, where the omega k, where the dimension of E intersect F is greater than or equal to k. This is kind of the first interesting type C locus. What's the formula for that? That's not so easy. We spent quite a bit of time. I found some formulas for it in terms of some Schubert polynomials, and Pragash found some others, and it was always got a little confusing. One reason is that when you find a formula in this setting, it's not quite so clear. So it's easy to see because you have this pairing that these Chern classes are not independent anymore. And so if I write down one formula and you write down another one, we might both be right. And we don't know which one is the right formula. Right? And, well, so I should say that if you know the answer to this, you know the answer to this question. That if you take E and E dual, you can form a vector bundle by taking E plus E dual. And if you take the graph of that map, it'll be isotropic. And you take E plus 0, and that's isotropic. And where those intersect will tell you exactly the rank of that. So in fact, if that's symmetric, it fits exactly with type C here. So the question was, how do you do this? And, well, Pragash was the first one that, well, first of all, yeah, I erased something. Fomin and Kirillov did a simple little thing with doing some algebra and said, you cannot solve this problem. So, of course, the claim I want to say is you can have all these properties from 1 to 8 and all the types, right? And so they wrote a paper and says you can't do that. And you can't even begin to do it. You can't find single polynomials, even for a simple case like B2 or something, with all the properties you would want. Right? So I'm claiming you can do it all. And it's, how do you get around all this trouble? So the one key thing, so I have to write these. So the main paper to look at for this is I think it's just a few years ago. So these, yeah, it comes from work of Pragash and Kazarian and Sarabilli and Mark Hyman and combinatorics. But there's a polynomial ring, which I think was familiar to Schur. Well, where you take some variables q's and you divide by these relations. So these are actually the relations that you see when you write down things like this. And this is free on the square free monomials. So you don't have any qi squares because you've gotten rid of that. So the claim is that there exists unique Schubert polynomials in gamma of xy. Okay. So W is in, well, Wn. So in type C, Wn is sign permutations and letters. But it's, and there's unique polynomials in there satisfying all the properties. So of course you have to modify them all to make them true. So they're homogeneous of degree equal to the length of W in that thing. And so what have I? You see what I've changed? I changed the definition of polynomial, right? So this is as good as a polynomial in any possible sense. It's as finite as can be. You can write down and compute with it. But it's not strictly in a polynomial ring. So it's not in Z of xy. It's in gamma of xy. And all these things are true. So it's stable. It doesn't depend on which Wn you're in. It satisfies this. In fact, the symmetry is simpler. When you take W inverse, you just interchange X and Y. The X's and Y's, I won't write them down, but they come from sub-bundles of the E's and the F's. The Chern X's and Y's will be the Chern classes of those. And the key thing is that Q is, I'll just write it, it's C of B over C of E, C of F. So let me give you just one example, is if you take W to be the simplest sign permutation, it takes 1 to minus 1, this is a locus where E meets F. And it's very easy to see that that's given by minus C1 of E minus C1 of F. And you'd be tempted to write that as minus the sum of the X's minus the sum of the Y's. But those go from 1 to n. Right? And you can't do that. It's supposed to be stable. Right? You can't. So in fact, the answer here is that this sigma W is, it's the first Q1. Right? So some of it, the Q's kind of stay stable as n goes to infinity, and the X's and the Y's act like in the type A case. So that there's a symmetry. The positivity is similar with, you have X's and plus Y's, and you have some Q's. They're called Q lambdas. They're Pfaffians. There's positivity of Graham, in fact, is completely general. It's for any G mod B. And then there are vector bundle interpretations of all these things. And there are vexillary. So what Dave Anderson and I have been working on recently is we found, besides this geometry, there a natural notion of vexillary ones. Those double Schubert polynomials, they're not given by determinants in type C, they're given by Pfaffians. So every place you see a determinant in type A, you look for a Pfaffian in type C. And there are also essential conditions. They're quite a bit more complicated than type A. But, and then the same is true in types B and D. If you know about those, you'll expect to see some halves, and you sweat a lot harder in type D. That's a general phenomenon. And types E and F, Dave Anderson did type G2, and E's and F, we have no idea how to do it. It's quite remarkable. Especially, what we want is not just formulas for loci in terms of flag varieties, but we want some algebraic geometry thing like this. This is not really talking about a flag variety, but they're bundled in any space with some properties and some symmetry. So in that case, you have symmetry. So what is it for type F4? We don't know. But the classical cases are done. Okay, that's done.
Any questions?
What do you mean by stability in the exceptional types?
So there's no stability there, right, of course.
But is there some compatibility between the classical cases and the exceptional cases, or even between the classical cases themselves?
So there's only one exceptional case where anything's been done. And so, I mean, one interesting thing in those cases is if you ask 50 people who are interested in exceptional groups what it's all about, you get 50 answers at least, right? I mean, so for example, I mean, everybody will know it has something to do with it. So like Dave, for type G2, there's some trilinear forms around. I don't think you're shocked by that, right? But what else is it? What is the geometry that you have? So all these things we call degeneracy loci. When you have bundles and maps and with these extra conditions, you want to have, for every element in the Weil group, you want a degeneracy locus. So because one thing to do to warm up is to look at the cohomology of the corresponding flag variety and work out the formulas. And the next thing to do warm up is to look at the equivariant cohomology of that and work out those formulas. And that'll give you these double things, which are much richer. And that'll determine the polynomials. But it doesn't determine the geometry. I mean, it's just in that flag variety. And it's surprisingly non-trivial to go from that to the general upper down.
Good questions? Thank you very much. So if people are interested in getting together later on, let me know.